September 12, 1883, Bridgeport, Connecticut. The engineering calculations scattered across Edward Payson Bullard's workshop table would have made European machine tool experts laugh out loud. American factory owner, attempting to solve the most persistent problem in heavy manufacturing using methods that violated 50 years of established engineering principles. Through the steam and grinding metal of his cluttered workshop, a crude vertical boring mill sat waiting for its first test. No horizontal spindle, no suspended workpieces, no traditional European design philosophy whatsoever. Yet it was about to machine a 450-pound locomotive cylinder that had defeated 3 of Europe's finest horizontal mills. In German factories, Schiess horizontal boring mills required daily bearing adjustments and weekly repairs. Each heavy casting created crushing sideways stress that bent spindles and destroyed precision. Most operations lost 40% of production time to breakdowns and maintenance. The Americans were attempting something the Europeans considered mechanically impossible: vertical orientation. Gravity as an ally instead of an enemy. Workpieces lying flat instead of hanging sideways. Manufacturing reliability that would eliminate the constant repairs plaguing every factory from Manchester to Munich. 4,000 miles from European workshops, the most decisive machine tool revolution in industrial history was about to prove itself, not through superior complexity, not through premium materials, but through one simple question that European engineers never thought to ask. Edward Payson Bullard stood in his cluttered workshop above Broad Street in Bridgeport, Connecticut, staring at the problem that had stumped the finest mechanical minds in Europe. At 41, he had spent years working for Colt and Pratt and Whitney, watching America's most skilled machinists struggle with the same fundamental challenge that plagued every factory from Manchester to Munich. The mathematics were brutally simple. When you machine heavy industrial parts using a horizontal boring mill, you must hang massive iron castings sideways on a horizontal spindle, creating mechanical stress that no bearing system could reliably handle. The workshop around him told the story of American manufacturing's dependence on European engineering. Scattered across his workbench lay technical drawings from German Schiess, horizontal boring mills, English Craven mills, and French Ducamoon machines. Every design followed the same principle that had dominated machine tool construction for 50 years. The workpiece hung horizontally from a spinning spindle, suspended like a massive pendulum that fought gravity with every revolution. Bullard had calculated the engineering reality in his leather-bound notebook. A 300-pound ship propeller casting, when hung horizontally, created mechanical stress equivalent to balancing a piano on a broomstick. The bearings could not handle it. The spindles bent under the load. The work fell. Beyond his workshop windows, the sounds of American industry revealed the scope of the crisis. Steam whistles marked shift changes at factories that operated on European schedules dictated by European equipment failures. A typical German Schiess horizontal boring mill handling a 500-pound locomotive cylinder created 2,200 pounds of sideways stress on its main bearings. English Craven mills averaged a breakdown every 14 operating days, requiring 6 to 18 hours of repair time that shut down entire production lines. Worker injuries occurred monthly as heavy castings slipped from their horizontal mountings, sending men diving for cover as tons of iron crashed to factory floors. Bullard pulled out his latest calculations, numbers that revealed why American manufacturing was losing the global competition. European machine tool exports to the United States totaled $2.3 million annually because American shops could not handle heavy work reliably. 67 American machine tool companies had declared bankruptcy in the past 5 years, unable to compete with established European manufacturers who had perfected horizontal boring technology over decades. The average American factory lost 40% of its operating hours to repairs, adjustments, and equipment failures that European engineers accepted as inevitable costs of precision machining. The technical specifications painted an even grimmer picture. Horizontal boring mills required daily bearing adjustments to compensate for gravitational stress. Weekly spindle alignments corrected the bending caused by suspended loads. Monthly overhauls replaced worn components that could not withstand the constant battle against gravity. The maintenance schedules alone made American manufacturing uncompetitive against European factories that had learned to build these costs into their production planning. Yet Bullard had been studying this problem for months, filling notebook after notebook with engineering observations that pointed toward an impossible solution. His sketches showed a boring mill turned completely upside down, with the workpiece lying flat on a horizontal table while the cutting tool descended from above. Instead of fighting gravity, the design would harness it. Instead of creating sideways stress on bearings, vertical orientation would compress loads directly downward into the machine's foundation. The concept seemed absurdly simple, which made Bullard suspect that every European engineer had considered and rejected it for reasons he had not yet discovered. The doubt crept in every time he examined his crude drawings. If vertical boring was possible, why had no one in 50 years of machine tool development attempted it seriously? The German workshops that produced the world's finest precision machinery employed hundreds of engineers trained in the most advanced technical schools. English machine builders had access to the mathematical knowledge developed during the Industrial Revolution. French manufacturers combined artistic precision with scientific methodology. These were not amateur inventors working in isolation above small-town workshops. These were the technical giants who had established the principles of modern manufacturing. The sound of footsteps on the wooden stairs interrupted his thoughts as Thomas Murphy, his lead machinist, entered the workshop carrying a letter from Hartford. The Hartford and New Haven Railroad had sent another inquiry about boring mills capable of handling heavy locomotive work. Their current horizontal mill, a pride of German engineering, had failed 3 times in the past month, attempting to machine a 450-pound cylinder casting. Each failure cost the railroad 12 hours of downtime and $50 in emergency repairs. They needed American alternatives to European equipment, but Murphy's expression suggested he knew what Bullard would tell them. Bullard walked to the window overlooking Bridgeport's industrial district. Smoke rose from a dozen factories equipped with European machinery that defined the limits of American manufacturing capability. Steam-powered horizontal boring mills occupied the centers of machine shops like mechanical altars to European engineering superiority. Their massive horizontal spindles dominated factory floors, demanding that all other equipment be arranged to accommodate their sideways orientation. Workers moved cautiously around these machines, knowing that bearing failure could send heavy castings swinging like wrecking balls through crowded workshops. The letter from Hartford represented more than a single customer inquiry. It symbolized American industry's recognition that European solutions were failing to meet American production demands. Railroad companies were expanding westward faster than European machine tools could reliably support. Steel mills required heavier machining than horizontal boring mills could handle safely. Naval shipyards needed precision work on castings too large for traditional European equipment. The market existed for better solutions, but the engineering establishment insisted that better solutions were impossible within the laws of mechanical physics. Bullard returned to his workbench and opened his notebook to the page containing his most radical calculations. A vertical boring mill with a 37-inch table could handle 2,000 pounds of work, lying flat versus 300 pounds hanging horizontally. Bearing stress would be reduced by 85% compared to horizontal orientation. The gravitational forces that destroyed horizontal mills would become stabilizing forces in vertical operation. The mathematics suggested that everything European engineers knew about boring mill design was not wrong, but incomplete. The workshop grew quiet as evening approached and the sounds of nearby factories faded to silence. Bullard stood surrounded by the evidence of American manufacturing's dependence on European engineering wisdom, knowing that conventional wisdom said his vertical idea would never work. He also knew that conventional wisdom was failing American industry every single day, creating opportunities for anyone bold enough to challenge 50 years of established mechanical principles. The weight problem that stumped Europe was about to meet American innovation willing to turn the entire world of machine tools upside down. The sweltering heat of summer 1883 turned Bullard's workshop into a forge as he began constructing his revolutionary vertical boring mill. Steam rose from the Connecticut River Valley, mixing industrial smoke with humid air that made every piece of iron too hot to touch without gloves. Thomas Murphy arrived each morning at 5 o'clock to find Bullard already bent over his workbench, assembling components that violated every principle of established machine tool design. The concept remained absurdly simple in its audacity. Instead of hanging workpieces horizontally where gravity fought every operation, lay them flat on a vertical table and bring the cutting tool down from above, making gravity an ally instead of an enemy. The first prototype emerged from months of careful construction, crude but functional in ways that challenged 50 years of European engineering doctrine. Murphy measured the completed machine with growing amazement at specifications that seemed impossible by horizontal boring standards. The table diameter stretched 37 inches, larger than anyone had attempted in vertical orientation. The spindle ran completely vertical, 180 degrees opposite to European design philosophy. Most remarkably, the machine's calculated weight capacity reached 2,000 pounds, lying flat compared to 300 pounds hanging horizontally from traditional mills. Bearing stress dropped by 85% compared to horizontal orientation, eliminating the crushing sideways forces that destroyed European equipment. The workshop buzzed with nervous energy as September 12th approached, the date Bullard had chosen for the first serious test. The Hartford and New Haven Railroad had delivered a 450-pound locomotive cylinder casting that had defeated 3 horizontal mills in their shops over the past 2 months. Each attempt had resulted in bearing failure, spindle misalignment, or catastrophic workpiece failure that sent railroad machinists scrambling for safety. The casting represented everything wrong with horizontal boring technology: too heavy for reliable suspension, too valuable to risk on unreliable equipment, too critical for railroad operations to abandon. Murphy positioned the massive casting on Bullard's vertical table with surprising ease, where horizontal mills required complex rigging, systems, and multiple workers to suspend heavy workpieces. The vertical design allowed gravity to secure the work naturally against the table surface. No chains, no clamps, no risk of the workpiece swinging free during cutting operations. The locomotive cylinder settled into position like it belonged there, its weight distributed evenly across the table's surface, instead of creating cantilever stress on horizontal bearings. At precisely 8 o'clock on that September morning, Bullard engaged the spindle and began cutting. The vertical boring mill operated with a smoothness that surprised even its inventor. No vibration transmitted through the workshop floor. No bearing stress warnings from monitoring gauges. No periodic adjustments to compensate for gravitational forces. The cutting tool descended steadily through cast iron that had resisted 3 horizontal mill attempts, peeling away metal shavings in long, continuous spirals that fell naturally away from the work surface instead of accumulating in horizontal spindle bearings. 8 hours later, the locomotive cylinder emerged from the machine completely finished to railroad specifications. Murphy ran his measuring instruments across the machine surfaces, finding tolerances that exceeded what horizontal mills achieved in twice the cutting time. The bearing temperatures remained within normal operating ranges throughout the entire operation. Tool wear measured significantly less than comparable horizontal cutting operations. Most importantly, the machine required no maintenance, no adjustments, and no emergency repairs during the entire machining cycle. Word of the successful test spread through Connecticut's manufacturing community with telegraph speed. By December, Bullard's order book contained contracts for 12 vertical boring mills from companies that had watched horizontal technology fail for years. The Colt Armory ordered 3 machines for heavy gun barrel work that had previously required sending castings to European shops. Singer's Sewing Machine Company contracted for 2 machines to handle casting operations that had shut down their horizontal equipment monthly. The New Haven Clock Company, despite working primarily with brass rather than iron, ordered 1 machine specifically to eliminate the reliability problems that plagued their foundry operations. The transformation in manufacturing capability became apparent within weeks of the first installations. Colt's Armory reported continuous operation for 36 days without maintenance on work pieces that had required daily bearing adjustments on horizontal equipment. Singer's production schedules stabilized for the first time in 5 years, as vertical mills eliminated the unpredictable downtime that had disrupted their manufacturing planning. Clock company supervisors discovered they could schedule precise delivery dates because vertical boring operations completed on time without equipment failures. Murphy documented the reliability statistics that would define vertical boring mill performance for decades. While horizontal mills required daily bearing adjustments to compensate for gravitational stress, vertical machines operated for months without mechanical intervention. Weekly spindle alignments became unnecessary because vertical orientation eliminated the bending forces that misaligned horizontal equipment. Monthly overhauls disappeared from maintenance schedules as bearing wear dropped to levels that measured within normal operational tolerances year after year. The financial implications became clear as 1883 closed and 1884 began. American manufacturers calculated cost savings that reached beyond maintenance reduction into fundamental changes in production planning. No longer did factory schedules include 40% downtime allowances for equipment failures. No longer did production managers maintain emergency repair crews for bearing replacements and spindle realignments. No longer did American companies send heavy machining work to European contractors because domestic equipment could not handle the loads reliably. Bullard stood in his expanded workshop on New Year's Eve, watching Murphy and 6 newly hired machinists assemble vertical boring mills that would ship to customers across New England and the mid-Atlantic states. Steam-powered machinery hummed throughout the building as American workers produced equipment that surpassed European technology through practical innovation rather than theoretical complexity. The order backlog stretched 6 months into 1884, representing demand that horizontal mill manufacturers had never satisfied reliably. Each completed machine carried specifications that challenged European engineering assumptions about the fundamental limits of boring mill design. The success created new challenges as quickly as it solved old problems. European machine tool manufacturers were beginning to notice American competition that achieved reliability levels their horizontal designs could not match. Technical journals carried reports of American innovations that violated established engineering principles, yet delivered superior performance in actual manufacturing applications. The question was no longer whether vertical boring mills worked better than horizontal designs, but whether American innovation could withstand the inevitable European response to technologies that threatened their industrial dominance. The spring of 1884 brought unexpected visitors to Bridgeport as news of Bullard's vertical boring mill success crossed the Atlantic. Heinrich Weber, chief engineer from the prestigious Schiess Works in Dusseldorf, arrived on the morning train with 2 assistant engineers and a letter of credit for $50,000. The German delegation represented Europe's most respected machine tool manufacturer, builders of horizontal boring mills that equipped factories from St. Petersburg to Barcelona. Weber carried instructions to investigate American claims of superior boring mill performance and either acquire the technology or prove its limitations before it threatened European market dominance. Bullard received the Germans in his expanded workshop, now employing 47 workers producing 2 vertical boring mills monthly. Weber examined the machines with methodical precision, measuring spindle alignment with instruments imported from Berlin, testing table flatness with granite surface plates calibrated to German standards, and documenting bearing clearances with micrometers that exceeded American measurement capabilities. His assistant engineers recorded specifications in leather-bound notebooks, comparing American construction methods to established European practices that had dominated machine tool manufacturing for 5 decades. The technical discussion revealed fundamental philosophical differences between American practical engineering and European theoretical precision. Weber questioned every design decision with mathematical rigor, demanding calculations that proved vertical orientation could achieve the accuracy levels required for precision manufacturing. He pointed out that American measurement tools lacked the precision necessary to verify claims of superior performance. He noted that Bullard's workshop conditions failed to meet the environmental standards maintained in German manufacturing facilities. Most critically, he argued that 6 months of operation provided insufficient data to validate revolutionary changes to established engineering principles. Weber's skepticism intensified when he observed American manufacturing techniques that violated German quality control procedures. Bullard's workers assembled machines using hand-fitted components rather than interchangeable parts manufactured to precise dimensional tolerances. Surface finishes achieved through American grinding methods appeared adequate, but measured rougher than German standards required. Tool steel selection relied on practical experience rather than metallurgical analysis that German workshops considered essential for consistent performance. The entire operation reflected American improvisation rather than systematic engineering methodology that produced reliable industrial equipment. The confrontation escalated when Weber challenged Bullard to machine the ultimate test piece, an 800-pound locomotive driving wheel casting that had destroyed two Schiess horizontal mills in Hamburg the previous winter. The German engineers had shipped the casting specifically to demonstrate the limitations of American equipment when faced with workpieces that exceeded the capacity of any boring mill design. Weber calculated that the casting's size and weight would reveal fundamental flaws in vertical orientation that lighter test pieces had concealed. Success would validate American claims. Failure would prove European superiority. Thomas Murphy supervised the positioning of the massive German casting on Bullard's largest vertical table, while Weber's assistants prepared measuring instruments to document the anticipated failure. The locomotive wheel represented everything challenging about heavy machining: complex internal geometries that required precise tool positioning, bearing surfaces that demanded mirror-smooth finishes, and dimensional tolerances measured in thousandths of inches across surfaces separated by several feet. European horizontal mills had approached this casting with extreme caution, knowing that bearing failure during cutting operations could destroy both workpiece and machine. The demonstration began at 9 o'clock on a humid April morning, with Weber observing every detail of American machining technique. Bullard's vertical mill engaged the massive casting with steady confidence, descending through iron that had resisted German horizontal mills for weeks. No complex workpiece suspension systems, no bearing stress monitoring, no periodic cutting interruptions to check spindle alignment. The American machine operated with mechanical simplicity that Weber found simultaneously impressive and disturbing, achieving results through practical design rather than theoretical precision. 11 hours later, the German locomotive wheel emerged from Bullard's machine completely finished to specifications that exceeded Hamburg workshop capabilities. Murphy's measurements revealed surface finishes of 32 microinches compared to 125 microinches achieved by German horizontal mills. Dimensional accuracy measured within 0.002 of an inch across all critical surfaces, performance that German equipment had failed to achieve after 47 hours of interrupted cutting operations. Tool life exceeded European standards by 300% due to the stable cutting conditions that vertical orientation provided. Weber's response revealed the depth of European resistance to American innovation. Rather than acknowledge superior performance, he dismissed the results as limited to specific types of machining work. He argued that chip evacuation would prove problematic on deeper cuts that American workshops had not yet attempted. He predicted that tool life would deteriorate under gravitational forces that vertical orientation could not eliminate. He insisted that spindle deflection would eventually compromise accuracy as cutting loads increased beyond current test parameters. Each technical objection reflected European confidence that established engineering principles could not be overturned by colonial improvisation. The German engineers' fundamental argument rested on theoretical foundations that had guided European machine tool development for 50 years. Horizontal boring mills had evolved through systematic refinement of proven design concepts, incorporating mathematical analysis and metallurgical science that American workshops lacked. Vertical orientation might achieve temporary success with favorable workpieces, but comprehensive testing would reveal limitations that practical experience could not overcome. European manufacturing superiority was built on systematic engineering methodology rather than empirical experimentation that characterized American innovation. Bullard ignored the theoretical criticism and expanded production to meet growing demand from American manufacturers who cared more about results than engineering pedigree. By late 1884, his factory workforce had grown to 47 employees producing machines that accumulated operational statistics European engineers could not dismiss. Customer satisfaction reports documented 0 returns and 0 warranty claims across installations that operated continuously without maintenance schedules required by horizontal equipment. Railroad companies, naval shipyards, and heavy manufacturing operations reported production improvements that eliminated dependence on European contractors who could not match American reliability. The success created international attention that worried European machine tool manufacturers beyond the Scheiss works. Technical publications carried reports of American vertical boring mills achieving performance levels that challenged fundamental assumptions about machining capability. Export inquiries arrived from England and France as European manufacturers discovered that American equipment might offer advantages their own horizontal designs could not provide. The question facing European engineering was whether to develop competing vertical designs or prove that American success was temporary aberration that systematic analysis would expose. Weber's cables to Düsseldorf reflected European industrial anxiety about American technological independence that threatened established market relationships. German machine tool exports to America represented millions of dollars annually in revenue that supported thousands of European workers. If American manufacturers could produce superior equipment domestically, the economic implications would extend far beyond machine tool sales into fundamental questions about European industrial dominance. The American vertical boring mill was becoming more than an engineering curiosity. It was becoming a symbol of industrial capability that could reshape global manufacturing relationships. The summer heat of 1885 had turned Bullard's expanded factory into a crucible of American industrial ambition when disaster struck during the most critical demonstration of his career. Captain James Morrison arrived from the Washington Navy Yard with procurement officers representing the United States Navy's most ambitious modernization program since the Civil War. Their mission was evaluating American machine tool capability for a massive contract worth $312,000 to equip 50 naval shipyards with vertical boring mills. Success would establish American manufacturing as superior to European technology. Failure would confirm that domestic industry remained dependent on foreign expertise for precision machining operations. The test piece Morrison brought challenged every assumption about vertical boring mill capacity. A 1,200-pound bronze propeller casting for the new cruiser USS Charleston represented the largest, most complex workpiece any American machine tool had attempted. The propeller's intricate blade geometry required cutting operations that pushed boring mill technology to theoretical limits, demanding precision measured in thousandths of an inch across surfaces that would determine naval vessel performance in potential combat situations. European horizontal mills had machined similar propellers, but only after weeks of careful preparation and multiple setup operations that American shipyards could not accommodate. Thomas Murphy supervised the positioning of the massive bronze casting with growing unease as naval officers observed every detail of the preparation process. The propeller's weight exceeded the tested capacity of Bullard's largest vertical table by 400 pounds, requiring modifications to the machine's foundation and spindle drive system. Heinrich Weber, still in America, documenting vertical boring mill operations, watched the preparations with satisfaction that bordered on anticipation. His cables to Düsseldorf had predicted that American equipment would fail when tested beyond the conservative limits that had characterized previous demonstrations. The demonstration began at 10 o'clock on a sweltering August morning, with representatives from Harper's Weekly and Scientific American documenting what they expected would be America's industrial triumph over European technological dominance. Bullard engaged the spindle with characteristic confidence, beginning cuts that would either validate 2 years of vertical boring mill development or destroy the credibility of American innovation in a single catastrophic failure. The bronze propeller responded to initial cutting operations with encouraging smoothness, generating the long spiral chips that characterize successful machining operations on Bullard's proven installations. Disaster struck without warning during the 4th hour of cutting operations when the main spindle bearing failed catastrophically under loads that exceeded its design capacity. The bearing failure transmitted shock waves through the machine's structure, causing the 1,200-pound propeller to shift violently on the table surface. The massive bronze casting broke free from its mounting fixtures and crashed through the table, destroying months of precision manufacturing work and sending fragments across the workshop. 2 workers suffered injuries from flying bronze pieces, though neither injury proved life-threatening. The machine itself was destroyed, beyond economical repair. Heinrich Weber's reaction revealed the depth of European satisfaction at American failure. Within hours of the catastrophe, his telegraph cables reached Dusseldorf with news that validated every skeptical prediction about vertical boring mill limitations. His message was succinct and devastating. American vertical principle proven defective under heavy loads. Recommend continued horizontal mill production. Bullard design fundamentally flawed. European technical journals would carry Weber's analysis within weeks, restoring confidence in established horizontal boring technology and discrediting American claims of superior engineering innovation. The industrial community's response was swift and merciless. Within 14 days, $127,000 in pending contracts were canceled as American manufacturers retreated to the safety of proven European technology. 3 competing American companies announced immediate return to horizontal mill production, abandoning their own vertical boring projects before similar failures could destroy their reputations. Railroad companies postponed equipment purchases indefinitely, unwilling to risk production schedules on unproven American innovations that might fail during critical operations. The financial devastation threatened to destroy everything Bullard had accomplished over 2 years of successful vertical boring mill development. His workforce dropped from 47 to 18 employees as orders evaporated, and suppliers demanded immediate payment for materials already committed to canceled contracts. The company's bank account, carefully built through months of profitable operations, drained rapidly as legal obligations exceeded incoming revenue. Sarah Bullard worked 18-hour days attempting to salvage contracts and negotiate payment extensions that might preserve the business through the crisis. The technical analysis of the failure revealed problems that challenged fundamental assumptions about vertical boring mill design. Post-disaster examination showed that the original bearing system, adapted from horizontal mill specifications, could not handle the concentrated stress patterns created by vertical orientation. The loads were indeed smaller in magnitude, but their concentration in specific bearing zones created failure modes that horizontal mill engineers had never encountered. European bearing theory, developed through 50 years of horizontal mill experience, simply did not apply to vertical orientation where gravitational forces acted differently on rotating components. Murphy's detailed investigation uncovered the engineering reality that Weber had predicted but could not prove mathematically. Vertical boring mills required completely different bearing designs that addressed stress patterns unique to vertical orientation. The oil circulation systems needed redesign to work with gravity rather than against it. Spindle dimensions required recalculation to handle concentrated loads rather than distributed stress. Even the table mounting system needed fundamental revision to prevent the catastrophic workpiece shifts that had destroyed the naval demonstration. The failure's implications extended beyond mechanical engineering into questions about American industrial capability that had motivated the vertical boring mill project from its inception. European manufacturers used the catastrophe to reinforce arguments that American innovation lacked the systematic methodology necessary for reliable industrial equipment. German engineering publications contrasted the Bullard failure with decades of proven horizontal mill performance, suggesting that American manufacturers should focus on assembly and production rather than fundamental machine design. Bullard stood in his damaged workshop, surrounded by the wreckage of 2 years' work, facing the possibility that European engineers had been correct about the impossibility of turning boring mill technology upside down. Orders that had stretched 6 months into the future had evaporated within weeks. Workers who had mastered vertical boring mill assembly were seeking employment with companies that manufactured proven horizontal equipment. The American dream of technological independence seemed as shattered as the bronze propeller fragments scattered across his factory floor. Yet the failure also revealed something that European criticism had missed. The 1,200-pound propeller had machined successfully for nearly 4 hours before the bearing failure occurred. The surface finishes achieved during those 4 hours exceeded anything horizontal mills had produced on similar bronze castings. The dimensional accuracy measured within tolerances that European equipment struggled to maintain. The failure was not in the vertical boring principle itself, but in bearing technology that had never been designed for vertical orientation. The question facing American innovation was whether the fundamental advantages of vertical machining justified the engineering effort required to solve problems that European horizontal mills had never needed to address. The bitter winter of 1885 through 1886 found Edward Bullard alone in his workshop, surrounded by the mechanical debris of his catastrophic failure, making the decision that would either vindicate American innovation or destroy what remained of his company's credibility. Rather than abandon the vertical principle that had shown such promise before the naval disaster, he chose to redesign his entire bearing system from the ground up. The European engineers were correct about one fundamental point. You could not simply adapt horizontal mill bearings to vertical orientation and expect them to handle completely different stress patterns. What they had failed to consider was whether American engineering could solve problems that European designers had never needed to address. Thomas Murphy remained loyal through the financial crisis, working without pay to help Bullard develop bearing technology specifically calculated for vertical loads. The challenge was unprecedented in machine tool engineering: create bearings that could handle concentrated downward forces rather than the distributed sideways stress that characterized horizontal mill operation. European bearing manufacturers had perfected their designs through 50 years of horizontal mill experience, but no one had systematic knowledge of how bearings performed under the unique conditions that vertical orientation created. Bullard was essentially inventing new mechanical principles, while his remaining competitors returned to the safety of proven European technology. The breakthrough innovation emerged through partnership with Bethlehem Steel, where metallurgists were experimenting with hardening techniques that exceeded German steel quality. Bullard's new bearing design incorporated tapered roller bearings specifically calculated for vertical loads, with steel races 25% harder than the finest German bearing steel available. The oil circulation system was redesigned as a gravity-fed lubrication network that worked with vertical orientation instead of fighting it, eliminating the complex pumping systems that horizontal mills required. The spindle itself grew 40% larger in diameter, with internal oil passages that provided cooling and lubrication directly to the cutting zone. The material revolution required collaboration with American suppliers who were willing to experiment with specifications that no European manufacturer would consider. Bronze caging incorporated self-lubricating alloy compositions developed specifically for vertical mill applications. Precision grinding techniques achieved 1/10,000th inch tolerance on bearing surfaces, accuracy levels that surpassed German manufacturing standards. The new table design featured cast iron construction 3 times thicker than horizontal mill standards, providing the foundation stability that vertical orientation demanded for heavy cutting operations. Through spring and summer of 1886, Bullard tested his redesigned machine with obsessive thoroughness that reflected his awareness that American innovation would not survive another catastrophic failure. The prototype underwent continuous operation testing that no horizontal mill manufacturer would attempt. 720 hours of uninterrupted cutting operations, equivalent to 30 days without stopping. Load testing progressed methodically from lightweight castings to 2,000-pound locomotive frames that represented the heaviest work any boring mill had ever attempted. Precision testing maintained 1,000th inch accuracy throughout extended operations that would have destroyed conventional bearing systems within hours. The reliability statistics that emerged from months of testing challenged every assumption about machine tool maintenance that European manufacturers had established as industrial standards. 0 bearing failures occurred during extended operation periods that would have required multiple bearing replacements on horizontal equipment. 0 maintenance interventions were necessary during cutting operations that would have demanded daily adjustments on European machines. The redesigned vertical boring mill operated with mechanical consistency that eliminated the unpredictable downtime that characterized every horizontal mill installation from Manchester to Munich. September 1886 brought the moment of vindication when Captain Morrison returned to Bridgeport with the same 1,200-pound bronze propeller that had destroyed Bullard's original machine. The naval procurement officers carried explicit instructions that reflected Washington's growing concern about American industrial dependence on European technology. The Navy needed domestic suppliers who could provide reliable heavy machining capability for the warship construction program that would define American naval power for decades. European contractors were expensive, slow, and potentially unreliable during international conflicts that might disrupt Atlantic shipping. The second demonstration began with tension that reflected everyone's awareness of the stakes involved in American technological independence. Bullard engaged his redesigned machine with confidence based on months of successful testing, but the bronze propeller represented challenges that laboratory conditions could not replicate. Naval officers observed every detail of the cutting operation, measuring surface finishes and dimensional accuracy against standards that would determine whether American manufacturing could support national defense requirements without European assistance. 18 hours of continuous operation proved the success of American innovation over European skepticism. The same bronze propeller that had destroyed the original machine was now machined to specifications that exceeded any horizontal mill performance documented in technical literature. Surface finishes measured 16 microinches, smoother than German horizontal mills achieved on similar bronze castings. Tool life extended 400% beyond European equipment standards due to the stable cutting conditions that properly designed vertical orientation provided. Most importantly, the machine required zero maintenance during the entire operation, eliminating the unpredictable interruptions that plagued horizontal mill operations. The orders that flooded back vindicated Bullard's decision to persist with vertical boring technology despite catastrophic failure and European criticism. The naval contract for 50 vertical boring mills worth $312,000 established American machine tool manufacturing as capable of supporting national defense requirements. Railroad orders for 127 machines over 6 months reflected industry confidence in reliability that horizontal mills could not match. International inquiries from England and France suggested that European manufacturers were beginning to recognize advantages that their horizontal designs could not provide. Construction began immediately on expanded factory facilities that would accommodate production demands exceeding anything American machine tool manufacturing had previously attempted. New hiring brought the workforce to over 100 employees trained in vertical boring mill assembly techniques that no European workshop understood. Sarah Bullard managed financial operations that projected revenues surpassing the most optimistic estimates from the company's founding. The backlog of orders extended into 1888, representing demand that European horizontal mill manufacturers had never satisfied reliably. By 1890, the statistical evidence was overwhelming. 847 Bullard vertical boring mills operated in American factories nationwide, achieving maintenance averages of 14 hours per year compared to over 200 hours required by horizontal equipment. The operational life of vertical machines exceeded 25 years without major rebuilds, while European horizontal mills required complete overhauls every 5 to 7 years. Customer satisfaction measured 97% reorder rates as American manufacturers discovered that vertical boring technology provided competitive advantages that justified premium prices. The final validation came through time itself, as the original Colt Armory installation continued operating into the 20th century. The same bearings, the same gears, the same cutting tools that Heinrich Weber had predicted would fail within months were still machining steel after 40 years of continuous service. German horizontal mills that had been proven superior in 1885 had been scrapped and replaced multiple times, while American vertical equipment continued generating profits for companies that had trusted domestic innovation over European expertise.